Okay, I'm gonna do this problem here. This time we're gonna use we're gonna use enable. I'll show you how that works. So here's the circuit. First, we'll derive the Boolean logic here. And we'll derive that by the input signals. We have A and Q go into XOR data produce A and Q is your output state value. This means it's a sequential logic. So it uses a clock. B and Q go into an OR gate. Producing Y, Z, X, and Y go into an AND gate. Producing Z. And then Z and enable producing your data. Okay, so I drew the clock for you. You could see this is the positive edge of the clock. This is the negative edge of the clock. And in this problem, we're using a active high synchronous reset. It's synchronous, meaning it's synced to the clock. So only at the positive edge of the clock will that reset work. And the state update is enabled only when enable is 1. Enable is a synchronous signal. So it only works whenever there's a positive edge of the clock. An asynchronous, like the reset, can be both synchronous and asynchronous, which means it could work on both edges, both the positive and the negative. But in this problem, we see that it's active high reset. So whenever the reset is 1, the reset equals 1. All the values, the state Q is cleared to 0. Positive edge. Every positive edge. And for the enable equals 1, then Q, the state, is updated like this with D. So we have to have for the data to pass like a gate, for the data to pass through the gate, the reset has to be for data to pass. Reset has to equal has to be low, it has to be off. and enable also has to be high. Signal has to be high. So the reset has to be off and the enable has to be high. So I made a diagram for you. So right here, the first positive, remember it's synchronous. So only on the positive edge of the clock will these work. So the first positive edge, enable, is 0. So no, that would not work. It doesn't this test. And reset is 1, meaning all the outputs are cleared. Here, it doesn't pass because both on this positive edge of the clock, both enable is 1 and reset is 1. Here, this positive edge, enable is 1. That checks. And the reset is low. So that works. So right here at this positive edge of the clock, your state variable would be updated. Okay, now what we're gonna do is we're gonna take this Boolean logic and we're gonna put it into a hardware description language, Verilog, and then synthesize this circuit. Then we'll test it like a over here with a test bench, which is like think of it like a flight simulator. So these here are your intermediate signals. A and B are your primary signals. So we're gonna put the primary signals are your primary inputs. You need a clock. So I gotta add a clock. You need a reset. And you need the enable. Oops. And you need your flip-flop. Register. Here's your intermediate signals are X, Y, Z, and D. Now we need our now the clock. Need a reset. Enable. Don't forget it's always at the bottom. So first we're gonna build the reset. If reset is 1, remember what we did earlier. It's the same thing as this. If reset is 1, that means if reset is 1, update the state variable. That's what this is saying here. Now, else if the enable is 1, oops, no, I did this wrong. Set 1 bit to 0. I said that wrong. If reset is 1, if reset is 1, set Q to 0. That reset equals 1, then state is clear to 0. Now, enable is the one that allows the path. Oh, that's great. There it goes. Okay. So your set, your enable, your button, your 2 primary input signals, your enable, synchronous enable, and your reset switch. There's the clock. Okay. And there's your gates, your XOR gate, your AND gate, your OR gate that we did right here. Now we're gonna write a test bench for this. Aye. Okay. For the test bench, write it. How do you say it? And now we have to write our signals. So here, when you're doing a test bench, notice how we're writing all the inputs as wires. When you do the test bench, it's the opposite because it's got to connect. Get your connector. Your inputs and outputs are exchanged because it's going to an external it's plugging into an external piece of external driver. So wires are A, B, clock, reset, enable. So now its register is A, B, clock, reset, enable. Wire is Q. Now we have to instantiate it. Instantiate. And we have to generate a clock. Console log the display. I'm just gonna use I'm not coding that, I'll just use generated code. Then we're gonna test all the possible combinations. So we have two inputs A and B, two inputs A and B. So that would be 2 to the second power. It's 4 possible combinations. But if there were four, it would be 8 possible combinations. And then there was 256 possible combos. If there were 8 inputs, it's 2 to the 8th power. So we can do a test with just write all the combinations with just 2 wires, but in an actual big circuit, you can't do that. All right. Now, that's it. So now let's instantiate is actual plugging the wires and together. That's what that means. Top module, circuit, UT. We plug in the first port A. B to port B. Clock, we plug in the clock port to the clock. The reset to the reset. The enable signal to enable port. Generate the clock. Always 5 seconds. Clock. Console display, I'll get that after. Oh, we gotta initialize it. Initialize all the state. Initialize all the registers and flip-flops to a known value. So you see right here, we want everything to be clear, so we know what the state of the circuit is at startup or at any particular time. So and we want to start just like we just did in previously. Start with the reset high so that everything is 0. Let's define enable. Enable. And then we'll do a 10 unit delay. 10 is 1 clock cycle. We'll do 2 clock cycles to allow to clear the basin. Another 20 seconds. And oh wait, got an enable too. So this could be this could be okay, never mind. Third power. Possible. So I forgot the enable. So got to count to 8 binary. Ah. That. Equals. This is 2 binary. This is 3 in binary. Let's do this quickly. Write the possible combinations from 0 to 8 binary like this. And we're going to do the display. For the sake of time. And we'll give a 40-second time. Finish. That's all the possible combinations of the inputs A, B, and enable. Syntax error. Not seeing anything. I think A2. What is wrong? Syntax and assignment statement element. Let's just comment it out, see what. There's a capitalized somewhere. Monitor is not. Unable to bind. Unable to bind. Unable to elaborate R value Z. Did I put? See. What did I do here? Wrong. Let's see here. Oh, the monitor thing. Okay, I see that. I think it's all from this display. Yeah. It's this display that I generated that screwed it up. That's why. Hold on, that was that display. Okay. Unable to bind where enable in top module. Unable to bind. Okay. Can't bind. Saying it can't bind. Did I screw it up? A.B cloud. Maybe I can't. Maybe there's some button enable and I don't know. Uppercase. Where's the uppercase? That's the first thing I look for. Ah, there. Okay, there we go. Now let's see if That's still throwing an error. Why is that throwing an error? What am I missing here? Ah, there's a semicolon. Okay. All right, here you can see that the reset doesn't go. The reset isn't low until 20 time units, 20 seconds, which is right. So that means when the reset is low, back to this, if reset is low, that's when data can pass. Because when it's high, everything's 0. So everything's 0. Everything should be 0 there. Or excuse me, not everything. The output should be undefined. But now, this is wrong. All these are undefined. Everything's undefined here. And it shouldn't be. Because enables 1. So I don't know why everything is undefined. I gotta ask you. Why is everything undefined? Oh, excuse me. Why are all my state outputs undefined? That I'm not sure. I think maybe I have to take the enable. Oh, I think I know why. Let's try to set the enable to 1. And then at 30 seconds, we get enable to, just how that works. Didn't do anything either. So I should have some value at state value. Your Q signal is not being drawn to output wire. I said output reg here. Ah, okay. Wait. So why? It says Q is not being driven. Should be. That should be right. says use a hold for my after the enable. That ain't work. I didn't think that would work. Let's see here. I don't do. Output wire. It's saying, I think that has to be it. I've done that before like that. Q is not connected in Testbench. Oh, I didn't know it. Instantiate the queue. That's right, saying I need this. Says I need to. I need to declare the output and the instantiation. I don't know why it's getting. Now, why do I get that error? Did I use Q differently somewhere? Always block on missing an end statement. Okay. Begin end. No. Here. There we go. Derp. Okay. Now Q gets updated here. Now that works. Reset. Where's enable is 1. Let's see where Q updates right here. Enable has to be 1 here. Yes. So it works. Doses.